You open an AI tool and ask for an image of a typical business office. Instead of a modern workspace, the system produces this, a 1950s boardroom staffed exclusively by men in gray suits. When you ask for a more contemporary version, the AI provides this, a black and white scene of vintage desks and typewriters. The model is effectively trapped in the data it was trained on. These outputs ignore the reality of a modern workspace, with its diverse teams, architectural spaces, and glass high-rises. This stems from a common mistake, viewing AI as an infallible calculator. When the model shatters that expectation, users often feel the tool is broken, but the model is actually operating exactly as built. To get better results, we have to look under the hood at the engine that drives its behavior. While artificial intelligence describes the broad field of mimicking human intelligence, machine learning is the specific engine that powers it. Machine learning does not rely on a database of explicitly programmed rules for every scenario. Instead, it learns by finding patterns in raw data. In supervised learning, a person labels the training data to teach a specific output, like identifying animals. Unsupervised learning removes these labels. The model analyzes an unlabeled dataset, discovering structural patterns on its own by clustering similar information together. Through pattern recognition, a model learns to identify a zebra's distinct visual signature, its specific black and white stripes, without being told what it is. The model then contrasts those patterns against solid-coded animals, like a horse, to build its internal map of the world. Finally, reinforcement learning refines these internal maps. Through a trial-and-error process guided by rewards, the model adjusts its strategy to improve its performance over time. Because a model's entire worldview is forged by this ingestion process, its capabilities are strictly confined by the specific data it was fed during training. This is the root of the biased office images we saw earlier. If the training data was historically skewed toward mid-century photography, the model will naturally reproduce those societal biases in its response. There is a knowledge cutoff, the exact point training data ends, freezing internal memory. While some models supplement with live web searches, their core knowledge remains static. This causes factual drift. As the world evolves past this boundary, the model disconnects from current events. However, you might also observe behavioral drift. When developers update the systems, the formatting, tone, or conversational style of the AI can shift unexpectedly, even when you use the same instructions. Since we cannot program these limitations away, we have to move beyond treating AI as an autonomous oracle and provide the necessary human oversight. We manage these limitations through strategic prompting, giving the machine the specific context and instructions it needs to overcome its data gaps. To defeat bias, you must provide fair and balanced references in your instructions. State the specific needs of your audience and provide the restrictive context the model needs to avoid falling back on stereotypes. You can bypass knowledge cutoffs and factual drift by specifying exact timeframes. Instead of asking about general trends, require the model to strictly use data from 2025. For complex tasks, use prompt chaining. By breaking a multi-step problem into sequential stages, you can steer the AI and reset its focus at every step. Approaching AI with this level of oversight changes the dynamic. You provide the direction the data lacks, guiding a capable colleague through a professional workflow. By applying these specific frameworks and chaining techniques, you overcome the data constraints of the machine. This active, responsible guidance is what transforms a restricted AI model into a true professional collaborator.